Chapter 25, Electric Currents and Resistance. In this chapter, we talk about electric battery, electric current, Ohm's law, resistance and resistors, resistivity, electric power, cold circuits, alternating current, microscopic current, current density and drift velocity, superconductivity, electrical conduction in the nervous system. Section 1. The electric battery. Volta discovered that electricity could be created if the similar metals were connected by a conductive solution called an electrolyte. This is a simple electric cell. So on the right we see we have two electrodes, one from carbon containing the positive charge and the other one from zinc electrode with the negative charge inside a sulfuric acid. And if we connect these two terminals to a voltmeter to read the difference voltage between these two, we will see there is a difference electric potential. A battery transforms chemical energy into electrical energy. Chemical reactions within the cell create a potential difference between the terminals by slowly dissolving them. This potential difference can be maintained even if a current is kept flowing until one or the other terminal is completely dissolved. Several cells connected together make a battery, although now we refer to a single cell as a battery as well. So here on the left we will see a demonstration of a battery which contains like a negative terminal and the positive terminal. At the bottom we have for the negative terminal the negative electrode zinc cup. On the top we have the top of carbon electrode, a positive terminal, which is isolated with an insulator, and they are all in the electrolyte paste. Section 2. Electric current. Electric current is the rate of flow of charge through a conductor. We define I as electric current. I bar, which is the mean value of the electric current, is delta Q, the overall the charges are flowing over a period of delta T time. Delta Q over delta T. The instantaneous current is given by I equals to dQ over dt, the derivative of charge over time. Unit of electric current is 1 ampere, A, which is equal to 1 coulomb per second. A complete circuit is one when current can flow all the way around. Note that the schematic drawing doesn't look much like the physical circuit. Here, the actual picture of connecting a lamp bulb to two terminals of the battery. And on the right, we have a schematic description or drawing of the circuit. So we see a bulb is connected to the positive and negative terminals of a battery, which is represented here. Electric current will flow from the positive terminal to the negative terminal. So, by convention, current is defined as flowing from positive to negative. Electrons actually flow in the opposite direction, but not all currents consist of electrons. So here we see, by convention, we say the current is flowing from positive terminal to negative terminal, but actually the electrons are flowing from the negative terminal to the positive terminal. Section 3. Ohm's law, resistance and resistors. Experimentally, it is found that the current in a wire is proportional to the potential difference between its ends. So we say I as the current is proportional to voltage or potential difference between the two terminals or the two ends of a wire. The ratio of voltage to current is called the resistance. So V over I is called R or resistance, or we can say I is equal to voltage over R, or alternatively we can say the voltage is equal to current I multiplied by resistance R. In many conductors, the resistance is independent of the voltage. this relationship called Ohm's law. Materials that do not follow Ohm's law are called non-ohmics. And the unit of resistance is the ohm with the symbol of omega. Capital omega, 1 ohm is equal to 1 volt over ampere. On top, we will see there is a linear relation between current and volts, which is an ohmic material. And at the bottom, we have the relation between current I and voltage V is not linear, so it's not ohmic. Standard resistors are manufactured for use in electric circuits. They are color-coded to indicate their value and precision. So here we have a cartoon showing that the resistors are being color-coded. So the first ring of color reads the first digit. For example, here is red. The second one is reading the second digit, which is green. And the yellow one is a multiplier, and the gray one is the tolerance. This is the standard resistor color code. Note that the colors from red to violet are in the order they appear in a rainbow. So the table demonstrates the color codes for the resistors, starting from black, represents number 0, and the multiplier by 1. Colored brown, for example, number 1, multiplier of 10 to the power 1, and the tolerance is 1%, and etc. to all the way to white, gold, silver, and no color. Some clarifications for Ohm's law. Batteries maintain a nearly constant potential difference. The current varies. Resistance is a property of a material or device. Current is not a vector, but it does have a direction. Current and charge do not get used up. Whatever charge goes in one end of a circuit comes out the other end. All right, now let's look at an example, problem number 6 from the book. A bird stands on a DC electric transmission line carrying 3800 amperes, which is demonstrated at this figure. The line has 2.5 times 10 to the power minus 5 ohms resistance per meter, and the bird's feet are 4 centimeters apart. What is the potential difference between the bird's feet? So we can find the potential difference from the resistance and the current. The feet are 4 centimeters apart, so the resistance is 2.5 times 10 to the power minus 5 ohm per meter multiplied by 4 times 10 to the power minus 2 meter, and this gives us 1 times 10 to the power minus 6 ohms. And from the relation between the Ohm's law, so we will have V is equal to current I multiplied by R. So we have 3800 amperes multiplied by 1 times 10 to the power minus 6 ohms. We have 3.8 times 10 to the power minus 3 volt, or 3.8 millivolts. Problem number 10 from the book as another example. A 4.5 volt battery is connected to a bulb whose resistance is 2.3 ohms. How many electrons leave the battery per minute? So we should use Ohm's law, equation 25-2, to find the current. Then we use the definition of current, which is charge per time, and calculate how many electrons will be leaving the battery. So let's say the current is voltage divided by the resistance, and it's equal to delta Q over delta T, which is time. And we have 4.5 volts over 2.3 ohms, and this is equal to 1.956 coulomb per second. So we say delta Q is equal to 1.956 coulomb per second multiplied by 1 electron, which is 1.6 times 10 to the power minus 19 coulomb times 60 seconds in 1 minute. And that gives us 7.3 times 10 to the power 20 electron per minute. Section 4, resistivity. The resistance of a wire is directly proportional to its length and inversely proportional to its cross-sectional area. So R is equal to rho resistivity times L divided by cross-sectional area A. So the constant rho resistivity is characteristic of a material. This table gives the resistivity temperature coefficients of typical conductors, semiconductors, and insulators. So for good conductors like silver and copper, we have low resistivity, as low as 1.5, 1.6-ish times 10 to the power minus 8, all the way to semiconductors and insulators like glass, for example, we have high resistivity of 10 to the power 9, all the way up to hard rubber of 10 to the power 15. For any given material, the resistivity increases with temperature. Rho T, resistivity, is equal to rho naught times 1 plus alpha T minus T naught. Semiconductors are complex materials and may have resistivities that decrease with temperature. All right, let's look at problem number 16 as another example. A certain copper wire has a resistance of 18.5 ohms. At what point along its length must the wire be cut so that the resistance of one piece is 4 times the resistance of the other? What is the resistance of each piece? Since resistivity rho proportional to length L, the length of the long piece must be 4 times the length of the shorter piece. So length should be 4 times the length of one. So we say total length is length of short plus the length of long, and this is equal to length of short plus 4 times length of short, and this is equal to 5 lengths of short piece. So the short piece length is 0.2 of the total length, and the length of the long piece will be 0.8 of the total length. So we should make a cut at 20% of the length of the wire, and we will have two pieces. One of them has 4 times the resistivity of the other piece. But what is the resistance of the short piece, for example, is the length is 20% of the total length. Therefore, the resistivity is 20% of the total resistivity. So we will have 0.2 times 18.5 ohms. This is equal to 3.7 ohm. Call this R short. For the long piece, this is 80% of the total resistivity, and that is equal to 14.8 ohms. Section 5, electric power. Power, as in kinematics, is the energy transformed by a device per unit time. So we say P is equal to derivative of energy U divided by T, which is dq dt multiplied by V. Or we simply say, by replacing dq dt as I, we say power is current I multiplied by voltage V. The unit of power is the watt, represented with capital W. For this, we can make the substitutions and say P equals I times V, and substitute V with IR for ohmic materials or devices, and that represents P as I squared R. Or we can replace I with V over R, and P will be given as V squared over R. What you pay for your electric bill is not power, but energy. The power consumption multiplied by the time. We have been measuring energy in joules, but the electric company measures it in kilowatt hours, or kWh. 1 kilowatt hour is equal to 1000 watt multiplied by 3600 seconds, which is 3.6 multiplied by 10 to the power 6 joules. Section 6. Power in household circuits. The wires used in homes to carry electricity have very low resistance. However, if the current is high enough, the power will increase and the wires can become hot enough to start a fire. To avoid this, we use fuses or circuit breakers, which disconnect when the current goes above a predetermined value. Fuses are one-use items. If they blow, the fuse is destroyed and must be replaced. So typically they have a metal strip inside, and if they blow, broken and should be replaced. Circuit breakers, which are now much more common in homes than they once were, are switches that will open if the circuit is too high. They can then be reset. So here we have a demonstration of a circuit breaker, which is composed of a side switch with a compressor spring and a bimetallic strip is controlling to have the metal strip to be in contact with the electric circuit, to have it in contact or have it open. So when it's closed, the circuit breaker is closed, and if the electric current is too high, the bimetallic strip will bend and causes the metallic strip to be disconnected, and the circuit breaker will be open. All right, let's look at problem number 32 in the book as an example. An electric car has a battery that can hold 16 kilowatt hour of energy, approximately 6 times 10 to the power 7 joules. If the battery is designed to operate at 340 volts, how many coulomb of charge would need to leave the battery at 340 volts and return at 0 volts to equal the stored energy of the battery's potential energy is equal to the charge times its voltage. So we say the potential energy of the battery, U, is equal to charge multiplied by its voltage. So we say Q is equal to potential energy divided by electric voltage. So we have 16 kilowatt hour, and that is equal to 1000 watts. To convert kilowatt to watt, and 3600ths of second in 1 hour divided by 340 volts, and that simplifies to 1.7 times 10 to the power 5 coulombs. Another example, problem number 44 from the book. A small immersion heater can be used in a car to heat up a cup of water for coffee or tea. If the heater can heat 120 milliliters of water from 25 degrees Celsius to 95 degrees C in 7 minutes, A asks approximately how much current does it draw from the car's 12-volt battery, and B, what is its resistance? Assume the manufacturer's claim of 85% efficiency. So for part A, we should convert energy, and the efficiency claim of 85% of the electrical power dissipates by the heater. That's the rate at which the energy is absorbed by the water. And we should recall that 1 milliliter of water has a mass of 1 grams. Okay, so for part A, we say 85% of power is emitted by heater, and that is the power absorbed by water. Okay, so 0.85 multiplied by IV, that's the power, and the power absorbed by water is the heat for heating water over time. And the Q for heating water is the mass of water times C times delta T divided by time. So we can solve it for the current. I is equal to MC delta T divided by 0.85 volts times T, which is time. Let's plug in the numbers. We have 0.12 kilogram of water. C of water is 4886 joule per kilogram. Delta T is 95 degrees C to from 25 degrees C divided by 0.85. Voltage is 12 volts and to 420 seconds. That gives us a current of 8.208 amperes, which is about 8.2 ampere. For part B, it asks about the resistance, and we should use the Ohm's law to find the resistance. So we say V is equal to current times resistance. Solve it for resistance. Voltage divided by current. We have 12 volts, 8.2 amperes. That gives us 1.46 ohms, almost 1.5 ohms. Section 7. Alternating current. Current from a battery flows steadily in one direction. Direct current, DC. Current from a power plant varies sinusoidally. Alternating current, AC. Here in the top we see the current over time, which is steadily having current all the time from a battery, for example. Let's call it DC, direct current. But in the lower part B, we see a current which is oscillating or alternating from a positive and a negative current of I naught, and that is called alternating current or AC. The voltage varies sinusoidally with time, and we as V naught times sine of 2 pi ft. F is the frequency, and 2 pi f becomes angular frequency omega. V naught sine omega t, as does the current. And we say I is equal to voltage over R, and if voltage is sinusoidally altering, so does the current. So we say I is equal to I naught sine omega t. By multiplying the current and voltage, we can gain the power. P equals I squared R, that is equal to I naught squared R sine squared omega t. As an average, if we take the average of sine squared over time, the average of sine squared is equal to 1/2. Therefore, the mean power, I squared R, is equal to 1/2 I naught squared R. Usually we are interested in the average power. P average is 1/2 I naught R, or 1/2 V naught squared over R. P equals 1/2 I0 squared R, or 1/2 V0 squared over R. The current and voltage both have average values of 0, so we square them, take the average, then take the square root, yielding the root mean square RMS value. I, or current RMS, IRMS, equals to square root of the mean of I squared, which is equal to I0 over root 2, and that is equal to 0.707 times I0. The same for VRMS, V root mean square, which is equal to square root of the mean value of V squared, and that is equal to V naught over root 2. That is equal to 0.707 V naught. All right, at this point, we'll look at problem number 50 from the book as an example. An 1800 watt arc welder is connected to a 660 volt RMS AC line. Calculate A, the peak voltage, and B, the peak current. So we should use the average power and RMS voltage relationship to calculate the peak voltage and peak current. For part A, for peak voltage, we say voltage peak is equal to root 2 times V RMS. That is equal to square root of 2, 660 volt, and that is equal to 933.4 volts, almost 930 volts. For part B, we use the definition of the power mean is equal to I RMS times V RMS, and this is equal to I peak divided by root 2 V RMS. So I peak is equal to square root 2 times mean power divided by V RMS. Let's plug in the numbers. I peak is equal to square root 2 times 18 times 1800 watts divided by 660 volt. That equals to 3.9 amperes as the peak current. Section 8. Microscopic view of electric current and drift velocity. Electrons in a conductor have large random speeds just due to their temperature. When a potential difference is applied, the electrons also acquire an average drift velocity, which is generally considerably smaller than the thermal velocity. As you can see here, if we apply electric potential between the two ends of the wire with a cross-section of capital A, almost constant electric field will be formed from left to right, and that is causing a current density J from left to right. We define the current density, current per unit area. This is a convenient concept for relating the microscopic motions of electrons to the macroscopic current. Little j equals current I over cross-section A, or current I equals J times A. If the current is not uniform, we should take the integral of current density J times dA. The drift speed is related to the current in the wire and also to the number of electrons per unit volume. dQ is equal to the number of charges N multiplied by charge per particle, and we call it N times V times minus E, charge of electron. And that is equal to minus N A V D delta T times E. As usual, we define I, current, as delta Q over delta T, and delta T cancels out, and we will have minus N times E, electron charge, times A, cross-section, times VD, drift velocity. So the electric field inside a current-carrying wire can be found from the relationship between the current, voltage, and resistance. As we defined before, I is equal to J times A, B is equal to E times L, R is equal to rho times L divided by A. And substituting 3 into Ohm's law gives V equals IR. So on the left we have EL equals to JA multiplied by rho L divided by A, which is equal to EL equals JL rho, and L's will cancel out. We will have E equals J rho. So if we define sigma as 1 over rho, J, the current density, is equal to 1 over rho E, electric field. And if we define 1 over rho as sigma, conductivity, J equals sigma E. Problem number 56 as an example. A 5.3 meter length of 2 millimeter diameter wire carries a 750 milliampere current when 22 millivolt is applied to its ends. If the drift speed is 1.7 times 10 to the power minus 5 meter per second, determine A, the resistance R of the wire, B, the resistivity rho, C, the current density J, D, the electric field inside the wire, and E, the number N of free electrons per unit volume. So for part A, just asking about resistance, let's use Ohm's law. And we have V is equal to IR, and solve it for R, V over I, plugging the numbers, 0.022 volt divided by 0.75 ampere. That is equal to 0.02933 ohms, which is equal to almost 0.029 ohm to its significant digits. For part B, ask about resistivity. Let's use equation 25-3, which says R equals rho L divided by A, and solve it for rho, RA divided by L, R squared divided by L. Let's plug in the numbers. We just obtained the resistance, 2933 ohms, times pi, and the radius is 1 times 10 to the power minus 3 meter squared, divided by the length of the wire is 5.3 meter. We will have rho equals 1.739 10 to the power minus 8 meter. Almost 1.7 times 10 to the power minus 8 ohms meter. For part C, we should use equation 25-11 to find the current density. That says J equals to I divided by cross-section of the wire, which is current I divided by pi R squared. If we plug in the numbers, we will have 0.75 ampere divided by pi 1 times 10 to the power minus 3 meter squared. That gives us 2.387 times 10 to the power 5 ampere per meter squared, almost 2.4 times 10 to the power 5 ampere per meter squared. For part D, we should use equation 25-16 to find the electric field. Say J is equal to 1 over rho E, and electric field is rho times J. It's equal to, we obtain rho from part B, that is 1.739 times 10 to the power minus 8 ohms times meter, multiplied by J from part C, we obtain 2.387 times 10 to the power 5 ampere per meter squared, and that gives us 4.151 times 10 to the power minus 3 volts per meter, almost 4.2 times 10 to the power 3 volts per meter. For part E, which asks about the number of electrons per unit volume, we use the absolute value of equation 25-14, says J N E drift velocity. Solve it for the number of electrons, J divided by electron charge times drift velocity. If you plug in the numbers, we have 2.387 times 10 to the power 5 ampere per meter squared. The denominator, we have the charge of an electron, 1.6 10 to the power minus 19 coulomb, multiplied by 1.7 times 10 to the power minus 5 meter per second. And that simplifies to 8.8 times 10 to the power 28 electron per meter cube. And this is number of free electrons per unit volume. Superconductivity. In general, resistivity decreases as temperature decreases. Some materials, however, have resistivity that falls abruptly at a very low temperature called the critical temperature Tc. Experiments have shown that currents, once started, can flow through these materials for years without decreasing, even without the potential difference. Critical temperatures are low. For many years, no material have found to be superconducting of 23 Kelvin. Since 1987, new materials have been found that are superconducting below 90 Kelvin, and work on higher temperature superconductors is continuing. Summary of Chapter 25. A battery is a source of constant potential difference. Electric current is the rate of flow of electric charge. Conventional current is the direction that positive charge would flow. Resistance is the ratio of voltage to current as V over R, which is the Ohm's law, or we can write V as I times R. Ohmic materials have constant resistance independent of voltage. Resistance is determined by shape and material. R equals rho times L over A. Rho is resistivity. Power in an electric circuit is I times V. Direct current is constant. Alternating current varies sinusoidally. I equals V over R equals V naught over R sine omega t, which is equal to I naught sine omega t. The average RMS current and voltage are defined as I RMS equals to the square root of I squared mean is equal to I naught over root 2, and is equal to 0.707 times I naught. The same definition for VRMS equals to the square root of V squared mean equals to V naught over root 2. That is equal to 0.707 times V naught. Relation between drift speed and current, I is delta Q over delta T, and is equal to minus NE A VD.